For the homework on day 16, the first one was sketch an example of negative feedback as stomach fills with food with an appetite neuron that would be inhibited. So we'll come back to the others, but let's start with the negative feedback. So we need an appetite neuron that I'll label AP, and it's going to trigger eating. And that is going to result in food going into a stomach. So here's a stomach. And as the stomach fills, it's going to stretch. Okay, so it's going to be inhibited as the stomach fills with food. So how does it detect that the stomach is filling with food? Well, stretch channels would tell you it's filling. There could be other things. You could use amino acids or something like that to detect them, but stretch neurons would tell you how full it's getting. So I'm drawing a dendrite here, and that's a stretch channel, so that symbol represents a stretch channel, and of course we know it's not going to be bigger than the dendrite. This is a sensory neuron, and I'll call this neuron B, just to keep track. Going to send that to an inner neuron. And then we've got to figure out how do we connect this and then how do we make it negative feedback. So we want as the stomach fills with food, we want to inhibit it. So let's draw something from here to inhibit it. Call this neuron C. And it's going to be an interneuron. And now let's think about whether we have what we need. First, any feedback system has to have a loop. The question is, do we have a loop? We've got eating. Well, the appetite neuron triggers eating, which means food, which means the stomach stretches. That stretch is detected by a stretch channel. Sodium comes in. That positive charge gets to the spike initiating region, starts an action potential, activates this inner neuron. This inner neuron has action potentials. That gets down and that inhibits our target. So we do have a loop. Oops. Try that again. The loop, the stretch, and inhibition, negative feedback. So something you always want to check is, do you have that loop? If you don't have a loop, it's not feedback. Okay, what about positive feedback? Let me erase my highlighting there. What about positive feedback? Let's do this in a different color. We've got the rate of feeding is normally slow and careful, but if the mouth receives or tastes food that's high in amino acids, then use a GPCR to detect it, have the neural circuit excite the appetite neuron. Okay, so we need a sensory neuron. Here we are in a mouse. So we'll make a giant sensory neuron because I need some space for my GPCR detecting amino acids. Here is a G protein. When our amino acid binds, subunit goes off. We'll have it activate adenylate cyclase. Here's our G protein subunit. That converts ATP to cyclic AMP. We'll have our cyclic AMP bind to and open a sodium channel. Sodium in. Okay, and that will let us start an action potential. Here's the spike initiating region. So we get an action potential. Now, where do we want to send that? So the rate of feeding is normally slow and careful, but if the mouth tastes food that is high in amino acids, here it is, have your neural circuit excite the appetite neuron. So we want our neural circuit. I didn't leave myself quite enough space. Here we go. Whoops. We want to excite the appetite neuron. And do we have a feedback loop? This one is a little more complex in the feedback loop, but let's run through it. So we've got eating going on. That eating is what's bringing the amino acids here. That's triggering action potentials in our in our sensory neuron and causing more action potentials in the appetite neuron. So we have positive feedback. The more eating, the more amino acids, the more action potentials. Okay, so the more we eat, the more amino acids, the more action potentials, the more neurotransmitters in this appetite neuron, meaning more appetite neuron action potentials. We do more eating and we trigger even more. So that's a positive feedback circuit with a cycle. When pain stretch neurons, so the same stretch channels can be involved in pain, this suggests, and it's true, are triggered by a very full stomach, they should inhibit the positive feedback. So let's make our stomach very full. And here's a nociceptor or pain neuron. We'll call it D. It also has stretch channels, but these stretch channels only open when we've stretched a lot, only when we've really stretched it. And then we want that to inhibit the positive feedback, so we could inhibit this neuron. And that would stop this response. It stops all that response right here. And so we never get the positive feedback. Now, how many neurons do you need to do? I deliberately showed an extra neuron here that you wouldn't absolutely have to have. You could go straight from the sensory neuron over to here. And I would count that correct, but you're better off including interneurons some of the time. That also means you're really flexible. The sensory neuron just needs to do one thing. You can have the interneuron do the next thing, go wherever it needs to go. That's what I could have done here. Let me add that. So I could have done this and then had an interneuron here. We'll call it E, that causes the positive feedback, and that would have been more realistic, that the sensory neuron, we go sensory neuron here to interneuron here to its target. And that's the first question.